projects with me. It's Paul Bowden, who's our technical resource manager at the School of Architecture and Built Environment. But Paul is a bit of a techie geek like me, and particularly in this field. So Paul does a huge amount of the work with me and alongside me on this. Just a little bit about me, if you haven't met me before. As Paul said, recently my title changed. I've spent nearly 24 years now in R&D in terms of the digital built environment, and sort of BIM and working in that. Before that, as a previous life, I used to work for Atkins, WS Atkins as they were then. I was an infrastructure engineer working on projects in the UK and Ireland. Most of my work is applied research and development, so I work a lot with companies, particularly in the UK, and predominantly through knowledge transfer partnerships. I think I've done around 16 of those. And in the past, we've run the Construction Futures Research Centre and a project called Stella. So that's just a little bit about me. What we're going to look at in the next sort of 40 to 45 minutes or something like that is what we mean by this digital measurement, what kind of technologies are out there, how they work, what they cost, important, what's the bottom line, what's the pound, shilling, pence on some of these, and some of them are fairly expensive, one might say. How quick are they? Because there's always a time cost trade-off between these technologies. And then what kind of data can we get from them in terms of measurement data, and the workflows that we use particularly, and we've kind of honed and refined over the years. We're still refining them. The technology is still evolving. We're still changing how we do things. We're still changing our workflows as we find newer and more interesting technology to work with. And then we'll look at sort of what we think might be accuracy and what we would then term relative accuracy between some of these things. So we're going to look through these. Hopefully it'll give you an idea of some of the things that are happening at the moment, give you some ideas, maybe things that you have heard of, maybe things you haven't heard of. We'll try and unpack some of them and put them in the context of some of the projects that we're working on. Now this kind of measurement of things and getting data from them and seeing how accurate it is, it's somewhat of a lifelongish obsession. For me, it started in the mid-90s in my undergraduate days, where the professor I was working with on my undergraduate thesis was a surveyor, and he had me for part of my thesis working on deriving data and checking accuracy of the Black Ven landslide, which is down in Dorset, which is the photograph at the bottom. And we were using photogrammetry techniques, so grid-based photogrammetry, which at that point was okay, but a little bit clunky in terms of the computerized methods. We just started to get them. That set me on the track of being more interested in this. It also had driven into me the difference between accuracy and precision from a surveying point of view, and that was driven into me quite hard, that things can be incredibly precise but not accurate overall, and things can be sort of accurate but not precise, and vice versa. And that's something to this day that we still sort of push into my students. And then I carried on some of that work on digital terrain modeling and capturing the ground and the earth and deriving quantities from that. And that led to, there's an article there back in 2001 that we published in the American Society of Civil Engineers. So this isn't kind of a new thing. This is almost something that's always at the back of my mind. This whole measurement, digital measurement, this whole, what is it? How accurate is it? What kind of technologies are there for it? Yeah, and I guess some might say, sadly, it's somewhat of a kind of lifelong now kind of obsession with me. Obviously, technologies have evolved. Technologies are continually evolving. You know, we've gone right through from sort of the theodolite tape into the very old photogrammetry tools, through the tape measures, and then we're into the modern day era, which is predominantly this side, but we're going to talk a little bit more around terrestrial scanning. Obviously, GPS is becoming far more impressive than it was, and we're into drone surveys, photogrammetries, SLAM-based data capture as well, which is quicker, starting to get more accurate, and even down to the thing that's in everybody's pocket with your phone and capturing measurements. So we're going to look at them, look at the workflows we use with them, and then do some kind of comparative analysis of the data that comes from them. And I'll show you some examples of that as we go along as well. So if I talk about one of our first approaches that we do when we're on site, sort of doing data capture, and the kind of go-to one for us, the main one we use, is terrestrial scanning, terrestrial laser scanning. Now that is built on LiDAR, light detection and ranging. So it's built on static scan point for us. We use this piece of equipment here, which is a Faro. There's also Leica, Trimble, and some others who produce these pieces of equipment. But LiDAR is based on it. It's time of flight, pulses the laser out, hits an object, rebounds the laser. If we know the time point that the laser went out, we know the time point that the laser returns back to the unit, to the head of the unit here. We know the speed of light. We know the time difference between it going out and coming back again. Therefore, we've got a distance measurement using the sort of time, speed, distance equations. In a nutshell, that's what we're doing. We capture that. This unit here will capture sort of up to 1 million odd points a second. So we're slightly better than the old disto days or a tape measure. But it will shoot out and it'll capture. Now these as well, pretty much all the scanners now, they're getting faster. They will, as well as capturing X, Y, and Z positions of things that they hit, and they are line of sight based machines. So whatever they see, they will measure. If it doesn't see it, it won't measure it. It's not Superman. It's not X-ray, which is one thing everybody kind of asks the first time you use it. Can it see through the wall? It's not that. But it will measure whatever it sees. Because of that, we have to move it around the points. And we move it around an object to make sure it can see everything. You'll see up on the building here we have, and down here we have things we call targets, and that's what we use to help us stitch these 4 pieces of the jigsaw together when it comes together. So we'll move the scanner around static. The scanner remains static, but we move it around, capture the object, capture the measurement of the building from different places, and then we come back and we piece all that together. And that becomes our point cloud and 3D data. So in terms of the one that we use, which is this one, it's the Faro S150. It will measure down to about 1.5 to 2 mil at 10 meters away. So you're getting into quite sort of accurate measurements. This one has got, the one that we use has got a range of 150 meters. There are units that go up to 350. There are units that go up to a kilometer. If you're doing sort of open cast mining type things, they will come, they'll go down to a kilometer. Depends on the power of the laser and what you're using it for. Some of the units now will go up to 2 million measurements a second, but obviously there's a time trade-off between that. So your time trade-off is the more measurements you want to collect, the longer your machine is going to be sat in a static position, spinning and capturing those measurements. So there's a trade-off there between how accurate or sort of how many precision points you want to collect and how much time you've got to spend on site. Normally, we set hours to around about 6 to 7 minutes per scan, and that captures the color image as well. So you'll see these sort of examples that are running on the screen at the moment. These are projects that we've done fairly recently. This one is a few miles from our university in Dudley. It's an old priory building, dates back to about the 8th, 9th century. And this one here is a Guildhall, which is in Walsall, about 25-minute drive from where we are. It's a project that we're working on at the moment. They're renovating project, but there is no data from it. It used to be a courthouse. It's been changed and converted over the years. There's no data for the design or the construction team to work on, and they needed something to be captured to give them a starting point, and we went out and captured that. That's captured with this unit. We went down and took points on that one because of the stonework on it, and because the stonemason needs to do some work on some of these features, these sort of gargoyles on the front and some of the columns on the front. We were taking that down to around about sort of 2 to 3 millimeters in terms of the point spacing. What that gave us at the end was some 3D data that we were able to share with the stonemason and share with the architects as well, which hopefully you can see that pretty well. And the links for this are there. I can share that, but it gives us a 3D model that's fairly robust in terms of the quality that you can see of how it works. So we've done that. Cost is the issue with that one. They are fairly high costs. The one that we use at the moment, this comes out now, it's around 40,000. The cost is dropping, I might add, that as with all technology, the cost curve is kind of slightly going down. Obviously, as the new technology comes in, it's up. Ours is a few years old now, so the cost of that is dropping. But overall, globally, I would argue that since we've started using this technology, which was back in 2007-8, the cost is, in real terms, dropping for some of this technology. But it's still high capital expenditure to get it. So you're looking at sort of around 40,000 for the unit that we particularly use. So that's the terrestrial side of it. The scanning side, one of the downsides with the terrestrial stuff is it's not labor intensive, I would say, but it's time intensive. You know, you're on site, you set up in one place, you have to move around, and they are static setups. Over the last, say, 3 to 4 years, we have evolved, and measurement technologies evolved into something that we call SLAM. So SLAM, for those who haven't heard of it, stands for Simultaneous Location and Mapping, SLAM-based technologies. Essentially, you're data capturing and you're measuring on the move whilst you're walking or driving. Even some of these units will fit on the back of a car or on the back of a dog if you've got the robot dog, which we play with sometimes as well. I shouldn't say play with, and the head of school's on here really, which we do very applied research with sometimes. We put them on there. We the concept of SLAM is that it's capturing data, but it's also localizing itself. So with the terrestrial scanners, they are in set locations, and they understand where the scanner is in relation to all the points that it measures. With the SLAM, you're moving, and so as you're moving, it's generating a map of what it sees, and it's localizing, it's positioning itself within that map, so it knows as you're moving where you are, and therefore it's think of it like when you walk into a building. When you walk into a building or a room, the first thing you do is you look around, even if it's subconscious, but you're looking around and you're figuring out where things are. So you're going to say, well, the door's over there, there's a wall there, and you're figuring out where you are in that space and where you exist in that space. That's exactly what kind of SLAM is doing. But at the same time, it's measuring it and it's building up the picture of it. It's also, I think of it like building a trail of breadcrumbs, so it knows where it's been. And it knows where you've been and where you've walked in that. There are different types of SLAM. There's what we call visual SLAM. So visual SLAM is where it's building up that 3D data set just from images, and there's LiDAR SLAM. So some of these units, the two that are on there, and I'll talk about those in a minute, have laser scanners on them. So at the same time as looking and building up a 3-dimensional data set based on images, it's also measuring it with a laser. as well on top of that. So and then it combines those two together to give you data. So there's some examples are here, some of the projects we've worked on. This was one we did back in the summer, which was an old built in 1984. The building is shaped like a molecule, an oxygen molecule. It's down in Windlesham, down in Surrey. The whole interesting building, fascinating building. The whole thing is built like completely like an oxygen molecule with kind of hubs and arms that go off like you would see a chemist draw that. It was one of the first buildings, as a step back, to one of the first buildings that was designed using very early, back in the 80s, three-dimensional data, the precursor BIM, if we want to call it that. At that point, it was called RUPAC, which initially started out as the Riyadh University piece of research to develop this 3D data, but then became RUPAC. So we use that, slightly bigger, you wear it. And this one is a VLX talk about, or the slightly smaller, which is one that's handheld. And that's project. I was in the bell tower of a 11th or 12th century church with that one. Nearly impossible to get underneath with the scanning unit and the tripod. You could, but it would be a pain. Whereas I was able to climb down into the bell tower with the SLAM on that one and capture sort of all the information about the structure, the walls, etc. underneath it with that. So much more portable, much smaller. This one, the handheld one here, which is produced by a company called Leica. It's called the BLK2Go. It's handheld. It is probably about 9 to 12, I don't know, 10, 12 inches high. Looks like a bullet, looks like I guess a pill capsule shape. But you hold it in your hand. It feeds data back to your phone as you're walking around with it, to give you a preview of where you are. It got a shorter range, so it's got sort of around a 25-meter range. It will measure points at around about plus or minus 10 millimeters. So you lose that and a level of precision, if we want, or relative accuracy between the points. Captures nearly 500,000 points, and it depends on how far you walk with it. And as you're walking, it's building up this 3D data set. This is a project you can see here. This was an old bank built early Victorian period that was extended. The quickest way to go in with that was to use this piece of equipment, walk around the building. Took me around about, to give you an idea, to capture all of that data, and this is just the inside of the building, but to capture all of that data on the inside in total took me around, I think it was 43 minutes to capture all of that on the inside. And that's sort of 3 stories. There's a basement in there as well. So 43 minutes, captured all this data. We'll talk about how the sort of SLAM compares to the Faro in terms of relative accuracy as well, but it captures it in color. You can see the color point cloud at the end of it. So it's not a 3D model, CAD model, if we want to call it that. It's pseudo that. It's just lots and lots of dots, measurement points. Cost-wise, for one of those, they've just bought a new one out as well, but cost-wise, for the one we use, we're looking at about 46,000 plus your software on top of that as well. And the software sometimes is the one that kind of becomes your revenue cost rather than your capex. The other one that we use, which is SLAM based, is this bigger unit. It's produced by a company called NavViz. You look like a stormtrooper, I guess, for those of you who are Star Wars aficionados, as you're walking around with it. But that unit has got 2 laser scanners on it and more cameras, more high definition cameras. The cameras sit around the top, laser scanner on the top, laser scanner on the side. And as you're walking, the cameras are doing what we call the visual SLAM. So it's picking up where you are visually, and the scanner at the top and the scanner on the front are measuring and spitting out measures. It's got a higher range, so those lasers will measure up to sort of 50 meters away, and they will measure points that are closer together. and it will measure more points per second, so it's about 1.2. This project here, if I just dial this back, this is 12th century church that we're doing. We're actually still working on this at the moment, but we've captured most of the data. But to give you an idea of the data set that you will capture from this piece of equipment, this gives you sort of the idea of the quality. And this one in particular is interesting. They're going to do some work on this, so they're really interested in the stonework again on this one. So we brought this into some of our other software now, and you can start to see the sort of the fidelity, the definition of the 3D data that we can pull out from that. So that's using this walkable, slightly heavier. Time is around the same. That you walk at slower than a walking pace, but it's still quicker than having static setups to take measurements, individual static setups. And onto something now that's a lower cost, but it's becoming, I guess, much more exciting and much more interesting, is the photogrammetry. Now, that's where I started doing work with sort of photogrammetry back in the 90s. But it is evolved now and it's becoming really sort of interesting. It's essentially just photographs. It's just image based. So image based data capture, whether it be with a camera, even a phone camera, an SLR camera, or with a drone. At the moment, we're using a DJI Mini 4, which is a low-cost drone, but it gives a great video and image feed, 48 megapixel images, 4K video files at 60 hertz, 60 frames a second. So we capture hundreds, well, actually thousands of images if it's a video file based on either of these, and we use software that's available, and the software, very intelligent bit of kit, but it will stitch those images together and build a three-dimensional model from those images, just from images alone. We do need to put some control measurements in to that to make it scale, because obviously images are arbitrary. So images will create a 3D model that is proportionate in relative to itself, the images, but it's not scaled perfectly. So we do have to put control in, some control points to make it scale correctly. But we end up with that church that I mentioned earlier. This model here is produced from the church and is produced only using images, just photographs on the outside. So no sort of terrestrial, no scan measurement. That model there, and we'll talk about the accuracy of relative accuracy of that in a minute, is produced just using images. Some of the software that we use is down here. So there's one by Bentley, 3D Zephyr, or the one that we're using heavily at the moment is this one, Capturing Reality, which is actually owned by Epic Games. So it's owned by the people who create the games engine Unreal, which is responsible for things like Fortnite. For those of you who've seen your kids or you've played Fortnite, it's the same people who develop that, and they are pumping money, huge amounts of money into the development of that, and it's getting better and faster and more accurate, and it's a real sort of exciting thing. So we use that. All that, as I say, is just captured from images alone. So we're starting to get a bit more excited about some of this technology. This is an example. This one is a building in Bilston, which is not far away from us, which has been redeveloped by an architect. There was no data for some of the roofscapes, so we flew just around the roof. That three-dimensional data set that you're seeing on the screen here is produced just from images, just from photographs, and you can see these white dots here are the drone position when it was taking the photographs, and it's built that 3D data set up just from the images on its own. I think there was something around, I think maybe 180 images in total that built up that at a little bit of processing time. And then I guess we're coming down to the ultra low cost versions now, are the things that are in a lot of people's pockets, which are the iPhone. Since 2020, with the release of the iPhone, on the iPhone Pro, they started to add this small LiDAR sensor. So if you can see, if the back of your camera looks like that, it's got a small LiDAR sensor on the back of it, a low power one, but nevertheless, it is doing a similar thing to what some of those other LiDAR pieces of equipment are doing. Obviously, an iPhone Pro, you're looking at about sort of £1,100 to £1,200 for one of those. Got a very short range. People are now developing apps, some of them free, some of them paid, where you subscribe for a month. But there's lots of apps. These are the ones that are on my phone at the moment that I'm using. And just from from walking around with your phone, it does that slam. It captures data using that. It uses your cameras, and the sort of output we could get from it. This was a castle that I was walking around, and it gives you this kind of three-dimensional data set, a measured data set from it. And if we just change that, you can start to see how it's created that kind of 3D mesh from there, and behind that then it will then generate points, so you'll end up with the same output that you would get from one of the scanning tools. So lower cost, talk about sort of the relative accuracy of comparing that to some of the high cost things in a minute, but it's in your pocket. It's in a lot of people's pockets. It's low cost, and you can do some of this data capture with free apps that are available. They're constantly being developed. So in terms of measuring from those, once you've got that data and you've captured that, you can pull off measurements. You can pull off distances, areas, volumes, the usual things that one could derive from three-dimensional data. Sometimes, in order to do that, we have to what we call mesh the point cloud, which comes back to that we saw a few minutes ago, where you saw the triangulates over the points. So it takes each of those measurement dots and it creates triangles and creates a mesh over it. That uses a process normally called a Delaunay triangulation, which looks at each point and then draws a triangle. The reason it uses triangles is because triangles tessellate to any possible shape. So that's the reason we get that triangulation. So sometimes we need to sort of mesh from that, but that allows us to start to generate. Now we're using that a lot on historic buildings. We're doing a lot of work, an increasing amount of work at the moment. We work through our National Brownfield Institute on a lot of the brownfield sites that we're looking at redeveloping. There are historic and heritage interest buildings on there. And we've been doing a lot of work in the sort of previous years on heritage BIM, which is the application of not just BIM in terms of 3D modeling and data, but in terms of widening it out to the technologies, and specifically using those for historic and heritage buildings. So heritage BIM is kind of a field in its own right. It originated back in 2009 with a guy called Maurice Murphy in Dublin, who coined the term and started to talk about sort of heritage BIM applications to heritage. It's on Historic England radar. They've started to produce their own sets of guides and documents to support the development of the use of BIM in heritage projects. And very often, the reason it's more interesting to us is it's challenging. There is no straight, there is no orthogonal when you come to heritage buildings. Sometimes they're all over the place, and they can create some really interesting challenges for us in terms of measurement and taking quantities from them. So some of the examples are on here. That's a cricket pavilion that we did in Worcester, which that actually is being translocated. So we measured it. We used the BIM process to deconstruct that building piece by piece, quantify how much needed to come down for the contractor, and then we put it on pallets and we moved it to a new place, and it's sort of in the process of being rebuilt. This one was an old memorial hall, or this thing at the bottom here was a project I was working on in Alexandria in Egypt. So capture some, I guess we're really into the historic stuff with that. So the example project where we've started to do some work, and I'll just show you some early results from this at the moment, is on this particular church, the Holy Trinity Church. Initial construction was 1189. It has gone through some various tweaks and changes throughout its history since then. It's based in Eccleshall and Stafford, but we have done various different measurement techniques on that, using all of the things that we talked about previously, the terrestrial scanning, the SLAM scanning, and the photogrammetry scanning. And we use a range of software for those. We use sort of Pharo-Scene, Polycam, which is an app, some of the Leica software, the NavViz, which is the wearable, and the reality capture, which does the photogrammetry. So we use a range of software. We can create various different file types for those. Particular interest is this one, this E57. For anybody who's into the BIM side of things, the best way to think of E57, it's the IFC of the scanning data sets. It's neutral, it's International Standards Organization, so it's not a proprietary file format, it's an ISO format. And then we use an open source piece of software called Cloud Compare, completely free, continually being developed by teams who are interested. We all of the new data sets together, and we can then run analysis to understand how they compare to each other. So what you're seeing there, this kind of coloured, it shows you where the deviations are between one data set and another one. So we've taken the terrestrial scanning, where the scanner is static in one position, and that's measured down on this project. We've measured that down to 2 mil distance between the points. We've taken that as our control, as the truth, if we want to call it that. And then we've compared the other data sets to it to see what difference we kind of get in that measurement. And we've got some interesting results from it. Now we're doing chunks of the building and sections. I thought today I'd just show you some of the small test zones that we've talked about, and we picked a buttress, one of the buttresses out of the side, and we've taken that sort of 2 to 3. It's somewhere between 2 to 3 mil overall. We've said that take that as a 3 mil, and what we've started to look at is where the surface deviates, how much difference there is between the other data sets, how the surface area we can derive from those differentiates, and how the volumes of stone within that buttress deviate as well. And I guess some of the results actually were fairly surprising to us as well, in terms of the quality that we've got. But the photogrammetry, so the model that we got on this side, which was just the photogrammetry, so just images, no laser measurement on that, that was just from images and then scaled using control. We compared that to the terrestrial scanner, sort of, 2 to 3 mil resolution. You can see down here the red is the highest level of sort of where it's deviated from the blue. The blue is the better one, but even at the worst case scenario, we were about roughly sort of 50 mil at the highest level, between sort of 25 and 50 mil. Most of that surface that we analysed was around about 10 mil difference, which, where this is just taken from photographs, was pretty good. A lot of the points actually were sub 10 mil difference in terms of the measurement. When we ran the analysis to pick up the surface area of the stonework, we ended up with overall the surface area was sort of 0.159 meters squared difference over all of that. And we were comparing like for like. Now, some of that might be some of these tiny little bits at the bottom, but overall, the area was that the volume came out. The difference between the volumes that we derived was sort of 0.04 meter cubed. Considering that has come from nothing but pictures, and is relatively quick to capture, that's not bad in terms of the difference between, you know, the cost difference and the time difference for doing the calculation. So that one kind of sparked our interest. We then started to look at the SLAM scans, and we got, as we kind of anticipated in terms of the deviation between the two, much closer in terms of the surface deviations and the surface measurements, which we would expect because it's using a combination of laser scan and photogrammetry and photograph. So more accurate. In terms of the deviation, you can see down there, most of the points were within sort of 25. So we're very, very close, and volume-wise, we're starting to get closer. The difference between the two volumes that came from the two objects are much closer. And we would expect that because the SLAM, the technology we use, which was the NavVis VLX, which is the wearable one, it's shooting out lasers and creating the photogrammetry. So from a measurement perspective, I guess more relative accuracy. I've said relative accuracy because we're comparing it back to this one, which is our control, which we can never say is 100% accurate because it's still interpolating measurements between every sort of couple of mil. The iPhone, we did the same thing with the iPhone measurement. We took that section out, and as we expected with the iPhone, obviously lower resolution data that's being captured, so we've got substantially bigger deviations in terms of the surface variation, and we've got bigger deviations in terms of the volumes that we can derive and the areas between the two. But we kind of have to put that into the context of we're using this thing, which, you know, keep it in our pocket, as opposed to a 40, £50,000 piece of equipment. So if we balance that cost versus relative accuracy, even that, it's still not bad. It's not horrific. So overall, looking at them, and this is kind of fairly early stage pieces of work, particularly on this project. And this one's interesting because it's got so many different changes to the structure over time, and you can read the building as well with a bit of sort of pathology on it. You can see where the parts of the building were added sort of during, you can see the Victorian additions, and you can see some of the earlier editions as well. So you're able to quantify. That's what we're starting to do with this, is look at those different elements of the building and quantify those different elements of the building. But see, you know, roughly it's, you've got different cost levels, different kind of accuracies, and kind of as we'd expect, that we've got some, you know, higher accuracy with the SLAM where the lasers are involved, higher than we anticipated accuracy with the photogrammetry and the drone based, and the lowest accuracy with the iPhone, which we anticipated. But you know, this is still, I guess, new-ish technology and new ways of working. But we also see that kind of cost level and time level and investment decrease, and speed. This is arguably the slowest. This gets quicker. I can take photographs really quickly, or if I've got my phone, I can just walk around it. So you kind of, the speed becomes all a trade-off, as with everything in life. We've got this kind of accuracy, speed, cost triangle and trade-off between them. So that just gives you hopefully a bit of an idea. It's one of those things at the moment we're kind of still playing with, and we're still finding new things, and we're still sitting there some nights looking at this stuff and going, right, what next? What do we do next? How do we compare it? What do we do with this? What's new coming on the horizon? And there are new things coming on the horizon. We've now, in terms of some of this 3D data, we're into things called NeRFs, which are neural radiance fields, which are that's way to describe them. They're using AI at the back end, so you can just have a couple of photographs, and the AI is figuring out what's happening with the rest of it. Right down to some of the latest technology that's coming out, something called Gaussian splats. And we've got one of the researchers looking at those in particular, which is a whole new way of creating that 3D data set, visual data set. And we've just got to do some work now in terms of what data we can get from that and how the relative accuracy of that is in terms of the speed. But that hopefully gives you an idea of some of the tech, some of the work that we're doing in terms of comparing the outputs from those bits of tech as well. It's ongoing work. It's continually ongoing, and we're continually trying it with different projects. So we seem to be having a bit of a run on churches at the moment. Some of the work we're doing through our Brownfield Institute is a lot of churches who are looking to sort of redevelop. So the geometry of those is becoming more interesting as you get into sort of Gothic style stonework and Gothic architecture styles. Then things start to get more interesting in terms of data capture and in terms of quantifying some of that, because you're not into any kind of uniform shape with any of those as well. So it's ongoing. We're looking to publish some of this work out once we've got some more results, and once we've got some more examples and some of the other things. So keep a watch out for that. We'll certainly publish that through Suzanne and the QSI as well for anybody who's interested. But if you're interested in any of this, feel free to reach out to me. I'm on sort of all the social media channels, or my email address as well. Feel free to reach out to me. I'm happy to always discuss this sort of stuff that we're doing and show you some of the latest stuff that we're doing as well. Hopefully that's been a little bit useful. Seen some things that maybe you didn't know, some things that maybe you didn't know, some things that maybe you've seen before or not. So I'll wrap up with that. And Suzanne, I'll hand back to you. If there's any questions, I'm quite happy to